So this lecture is going to be on the climate change, the extra topic that we've added here. And I think what many of you need to begin thinking about is what climate is and what climate is not. So as we talk about climate change, we're going to look at it with numbers, and we're going to call this kind of a quantitative perspective. That climate is the long-term average of a host of features around the world. Among the variables, temperature is arguably the most fundamental. It governs evaporation that drives the water cycle. It controls cloud formation, and the contrast in temperature creates winds. So let's just say that temperature is kind of a key ingredient. Not the only ingredient, but a key part. So it all starts with the sun. The sun is what's driving surface processes. So the sun has this radiation, and that sunlight that enters our atmosphere, some of it immediately gets backscattered, right? 5% is lost to space, as we see here. There's 30% that's lost to space by reflection and scattering as well. So we've got this total 30% net loss right off the top. And most of that is just kind of re-radiated back. However, 50% of it is directly in diffused radiation that is absorbed by land and sea. And therefore, it's roughly a 10 to 20%, I think it's here's 20% is absorbed. So 20% goes into the atmosphere, is absorbed by clouds, etc. Roughly 50% is absorbed by land and water, so that's 70%, and then the rest of the 30% that's missing from the total energy budget is reflected back into space. So if you just kind of think of it in terms of the numbers, the quantitative part, we're looking at the 70% stays in the atmosphere and 30% is lost. So we've got a couple different ways we can observe or kind of characterize objects. And we can call, some of them are specular. This is where it reflects back as a beam of equal intensity. Where diffuse, this is where light gets reflected back as something that's weaker, that's traveling in different directions. So specular just tells you that objects like water kind of act like a mirror. They reflect a lot of the heat energy back. Whereas land is going to absorb a little bit more. It's going to reflect a lower frequency back. So moving on. So if we follow these numbers, roughly 50% is absorbed by the Earth's surface, 30% is reflected back into space, and therefore 20% is kind of absorbed and held by the cloud. So that's this absorbed part by the atmosphere. So this is where we're going to begin talking about, well, different surfaces, right? Dark objects hold heat while light objects act as mirrors and reflect heat. So this is what we're going to be using the term, this picture here, albedo. That darker objects hold on to this heat, reflect less energy, and lighter objects act more like mirrors and reflect more of the energy. We're going to be using this term called albedo. So because we're quantifying this, we're going to go ahead and take a look at, well, what's happening? Well, when we talk sunlight, we're really talking about the electromagnetic spectrum, and this is full of a wide range of wavelengths. The Earth and the atmosphere almost completely emit this long wave radiation. This is thermal infrared. This is essentially heat. The radiation emitted by the Earth is largely absorbed by atmospheric gases. And this is key here, atmospheric gases. And these are called greenhouse gases, GHGs. And these include carbon dioxide, methane, nitrous oxide, water vapor. We could even throw in carbon monoxide, but at a much lower percentage here. So we've got this CO2, and this is going to be one of the key ingredients that we're going to be studying in this unit, and it's carbon dioxide, and it is indeed a greenhouse gas. And that we have the surface and our atmosphere that are kind of managing this heat budget, where some of it is lost to space, but what's happening in the kind of a critical element to the whole climate change and conversation is, as we continue to burn fossil fuels, we are creating more carbon dioxide gas, and carbon dioxide gas is holding on to more heat that gets absorbed into the atmosphere. So we immediately see that there's a problem. So when I move on here to the concept of albedo, this is the reflectivity of a surface. This is the measure of an object's reflection of the sun's radiation. In astronomy, many planetary bodies in the solar system are visible due to the reflection of the sun's light off their surfaces, which is why we can see certain planets. So different objects have different lightness and or darkness. So light, right, fresh snow is about 80 to 90% reflectivity. That's the percent reflected. So the moon doesn't reflect much at all. It actually absorbs a lot, but there's some that gets reflected, and the moon actually has a surprisingly low albedo of 0.12, where asphalt, in this case asphalt here would, if we read a little bit more about this here, 0 for completely dark. So we're really talking the lower, the darker the object. That asphalt would have very, very low albedo, and 1 would be completely bright. So we're learning the concept of albedo as a part of this, and here's how this applies. Albedo applies by driving these feedbacks. A negative feedback is what causes stability in a system by offsetting the variables that are changing. Example, a rise in cloud cover on the Earth's surface due to warming can increase the amount of sunlight being reflected back into space, therefore decreasing the amount of heat energy added to the Earth's system. Where a positive feedback loop causes instability by increasing the magnitude of the variable that's changing. So during an ice age, continental glaciers reflect more sunlight, therefore even further cooling those conditions. So before we jump and completely dive into what climate change is, there are 5 key ingredients to what's driving climate change. And you can see them here: plate tectonics, Milankovitch cycles, ocean circulation currents, solar radiation, and atmospheric composition. So plate tectonics, these are how the continents are actually in slow motion. They're moving. These alter current and overall heat distribution on the planet. Milankovitch cycles are simply the motions of the Earth. Planetary motions have variability over large scales of time. You've got eccentricity, obliquity, and precession. We can't ignore that the Earth's location in space relative to the sun is going to be influenced by these planetary motions. We've got ocean circulation. Heat redistribution from the equator to the poles affects weather patterns and how much heat is absorbed. We've got solar radiation. The sun cycles in about 11-year periods, and we can refer to this incoming sunlight as insolation, incoming solar radiation. And last but not least, atmospheric composition. This is the chemistry of the atmosphere, where we have fluctuations in greenhouse gases, and in particular, carbon dioxide. Here we've got methane and water. But really, the concept, the argument that you're going to be needing to hear and learn about really pretty much is driven by what is happening to the carbon dioxide in our atmosphere. And that really becomes the argument or the conversation that is driving climate change, and are humans doing the changing of the climate.